Hey everyone, today we'll be doing problem number 15. An n-turn circular coil of radius r is suspended in a uniform magnetic field B directed vertically upward. The coil can rotate about a horizontal axis through its center. A mass hangs by a string from the bottom of the coil. When a current I is put through the coil, it eventually assumes an equilibrium position in which the perpendicular to the plane of the coil makes an angle theta relative to the direction of B. Find theta and draw a sketch of the coil in its equilibrium position. And these are all the givens. Alright, let's begin by drawing a diagram. They said the B field was vertically upward. So what I'm going to do is just draw a bunch of lines straight up, and that will represent our B field. Vertically upward. And the coil, what we're going to do is do a cross-section of the coil. Because by vertically upward, you could say, out of the page, and then you might have pictured it like this, where you're looking at the coil from the top down. Well, you can see that I took this and kind of, shifted the view. So now our B field is going up, and I'm going to give you a cross-section of the wire of the coil. And the reason why it's tilted like this is because there's a mass hanging on it. That's why it's tilted. And they said the axis is through the center. Again, this is a cross-section of the coil. You take the coil and you're looking at it from the side. Now, you need to recognize that, this is R. And you also need to recognize that you got theta here. And what I did here was, this is theta, and that's like how much it is tilted. It's tilted by that much, which happens to be the same here, and which happens to be the same here. We'll be needing these things soon. Okay, so there are two forces at play here. The magnetic force due to the B field, and the force due to gravity on that mass. And these two forces will be providing a torque on this coil. But these torques will be equal to one another, since the problem says that this eventually comes to rest at an equilibrium position. So we'll say the torque due to the mass equals the torque due to the magnetic force. And you know that the torque, for any regular object on the rod or something, it's just RF sine theta. You know that? And you know that the torque due to magnetic force on a wire or something is mu crossed with B. So, you know that mu equals NIA, number of loops times the current times the area. And now we're just going to plug it in. So I see RF sine, instead of just theta, I'm actually going to put theta plus 90, because I'm actually referring to technically this whole theta, which is that 90 degrees plus that theta, which relates to the force of gravity on that mass. So that's what I'm going to call theta plus 90. I'm say equals number of loops, current, area, NIA. And whenever you cross something, the magnitude of mu cross B would be mu B sine theta. So then I will write NIA B sine theta. Okay, moving on. I'm going to rewrite F as mg, because we're talking about the force of gravity and the mass. So I'll write Rmg. And without going into too much detail, I will say that sine theta plus 90 is just cosine theta. And then, just write everything else. So at this point, we're just solving for theta. So what I'm going to do is divide both sides by cosine, and then divide it by NIAB. So you'll end up getting tangent theta equals Rmg over NIAB. But this time, in place of A, you got to write pi r squared, because we're talking about the area of that thing. So I'm going to say Rmg over Ni pi r squared B. One of the r's cancels out. And now all we got to do is plug everything in and do arctangent. So I'll say theta equals arctangent. Mass of the thing, 0.5 kg, that's a given. 9.8 meters per second squared, divided by n, number of loops is 10, 1 amp, pi times the radius in meters, and then multiplied by how many teslas of that B field, and put this in your calculator, and you'll get theta equals 72.22567 degrees. This is how you do problem number 15.